This video is sponsored and approved by CuriosityStream. How do you find something when you don't know what you're looking for? Not only that, you don't know where to look for it either. That is exactly what faced particle physicists in the past 50 years during their hunt for the elusive Higgs boson. Okay, so by now you've hopefully seen my other video, the first one in this series, that talked about the history of the theory of the Higgs boson and where it came from all the way up to the 1960s. So after those now very famous 3 papers were published in 1964, raising this idea of this invisible field that permeated all of space, that put drag onto particles to give them mass. And also, I should say here, I don't think I made this clear in my previous video. The Higgs field is what gives the tiny fundamental particles, the smallest things you can get down to, it gives them mass. It doesn't necessarily give us mass. So for example, a proton, which is sort of the particles that you find in atoms that make up us, are made of 3 of these tiny fundamental particles called quarks. And if you add up the mass of all 3 of those individual particles that they get from this Higgs field, it's not as massive as the proton, because you also have a huge amount of energy that goes into binding those 3 particles together. And energy is equivalent to mass. E equals mc squared, that famous equation. So a lot of our mass that comes from atoms and protons and neutrons comes from the binding energy of holding those fundamental particles together. But those fundamental particles have mass because of the Higgs field that was predicted in 1964. Then in 1966, Peter Higgs came out with another paper and said that if this Higgs field is real, and that is the real mechanism that gives these fundamental particles mass, then there should be what's called a boson that communicates that information to us. So a boson is anything that communicates information about a field. So a photon of light is a boson because it communicates something to us about the electromagnetic field. And so in 1966, Peter Higgs suggested that maybe if we were going to prove that the Higgs field existed, then we should look for the Higgs boson. Now, this boson was predicted to be massive. Now, when I say massive, I mean massive to a particle physicist. You know, like, we're not talking massive on human scales or even astrophysical scales. You know, as an astrophysicist, massive to me means like 1,000,000 times heavier than the sun, whereas massive to a particle physicist is like 200,000 times heavier than an electron. So how do we actually go about detecting these massive Higgs bosons? You know, are they always there in the air around us, or do we have to produce them somehow in order to be able to detect that they're there? Well, lucky me got to go to CERN about 6 weeks ago now, and I actually got to sit down and chat with a load of particle physicists, and you bet I asked them this question.
So everything we do here at CERN happens around us anyway. So cosmic rays that come into our atmosphere create these kind of particle collisions. And so Higgs bosons are forming in our atmosphere, and they're happening in lots of other astrophysical situations. But we want to be able to measure them. And the best way to measure them is to do it in a very controlled way. So here at CERN, we have the Large Hadron Collider, our favorite particle accelerator, and we take protons, we accelerate them to the speed of light, we smash them together, and we use E equals mc squared to take this energy and create new matter. The Higgs bosons are created, so it's a statistical chance of what will be created. We never know, but our calculations tell us how often it should happen. And then again, they will change into other particles because they don't live for very long. They're what we call unstable.
So we're not necessarily looking for the Higgs boson directly. We're looking to make one and then look for the things that it decays into that we can detect. But if we're going to do this, we have to put enough energy in so that the energy we get out is enough to make one of these particles. Remember, energy and mass are equivalent. So the way that particle physicists usually say how massive a particle is to refer to it in terms of energy. So they'll often say that an electron, for example, is 0.511 mega electron volts. So mega meaning a million, and electron volts is a unit of energy. It's equivalent to 0.00000000008 joules. It's very, very tiny unit of energy. And really they should write mega electron volts divided by c squared, because that's how you technically convert it to like kilograms. But it's much easier and shorthand to write it as just mega electron volts, and everyone knows that you're supposed to just divide by c squared. So how this works for the Higgs boson is that you make a Higgs boson and then it decays into something different. So for example, maybe a pair of particles, a particle and its antiparticle. And you measure how much energy those two particles have, and you work backwards from there to work out how much energy the thing had that created them. So if there's one particle that's created that pair of antiparticles like crazy, we should see this huge big peak at the energy or mass of that particle. And if that peak is at an energy we've never seen before, then we know that we've discovered a new particle. The thing is though, particle physicists didn't know the exact mass or energy of the Higgs boson, so they didn't exactly know where to look. There was this huge range of energies that it could be in, and they didn't know how big of an energy it maybe could have and how far they had to push it. So much of the focus from the 1960s onwards was building ever bigger and bigger particle accelerators in the hope of getting to higher and higher energies so that maybe they would be able to produce and then detect a Higgs boson. Now, spoiler alert here, just for context, so that when I'm saying numbers later in the video, you understand of sort of like where we're trying to get to. When it was eventually discovered, the Higgs boson had an energy or a mass of 125 giga electron volts, or billion electron volts. So in 1966, there already was a working accelerator at CERN. It was called the proton synchrotron, and it had been working since 1959, and it could reach energies of 28 giga electron volts. A proton is about 1 giga electron volts in energy, just for comparison. And it was the world's most energetic particle accelerator at the time, but it didn't hold that title for long, because later in 1966, the Stanford Linear Accelerator was switched on, accelerating electrons up to 30 giga electron volts along a 3-kilometer long straight tunnel. It's still in operation today, and it's the largest linear accelerator in the world still. It's been responsible for 3 different Nobel Prizes, including proving that protons and neutrons were actually made of even smaller particles, that were actually the real fundamental smallest things that you could get to, that we now call quarks. But even though it is the world's largest linear accelerator, to this day it still doesn't have enough energy to produce a Higgs boson. Into the 1970s though, and it really was time for circular particle accelerators to shine, because you can reach much higher energy with those. So including the Tevatron at Fermilab in Illinois, USA. The clues should be in the name here. Tevatron, i.e. this particle accelerator was designed to eventually reach energies of 1,000 giga electron volts, or a teva electron volt.
Hello, yes, editing Becky here. Pretty sure I just said teva electron volts when I definitely meant tera electron volts. Let's hope I don't do that again all the way through this video.
It wasn't long after that, later in 1976, the super proton synchrotron was switched on at CERN, that was also then reaching energies of 400 giga electron volts. Now, when I talk about these energies, I'm talking about in a single beam of particles going around these accelerators. But often they have 2 beams of particles going in opposite directions, which they then bring together to collide. So if you collide one beam going in one direction and one beam going in the other direction, both with 500 GeV, then you're going to have a resultant energy of 1,000 GeV, or a teva electron volt.
Look, words are hard, okay? I just keep saying teva electron volt throughout the rest of the video, and let's just all pretend it doesn't happen, okay?
In 1986, the Tevatron finally managed to reach its peak energy of 900 giga electron volts per beat, meaning that its total energy was 1.8 TeV. It was around this time that the Large Electron Positron Collider started to be built at CERN, what came to be known as the LEP. They were building this new large circular accelerator in a 27-kilometer tunnel 100 meters underground. Now that tunnel is what hosts today the Large Hadron Collider, or the LHC, the very famous accelerator at CERN. But in the 80s, at the time, it was hosting the LEP, which could reach energies of 208 giga-electron-volts per beam. By 1995, the Tevatron at Fermilab had managed to confirm the existence of the top quark, the absolute heaviest of those most fundamental particles that are the basic building blocks of the universe. And this was a real boost to the hunt for the Higgs boson, because A, it was sort of a relief that we could produce something that heavy in these particle accelerators, but also because it was a prediction of the best model of particle physics, of which the Higgs boson sort of underpinned everything. So at this point you might be thinking, Becky, you said the eventual mass of the Higgs boson that was found was 125 GeV, and now we've got particle accelerators in the mid-90s that are reaching 1,800 GeV, or 1.8 TeV. So why hadn't the Higgs boson been found yet? Because you'd put enough energy in to get that energy out. Well, the thing is, the production of the Higgs boson is incredibly rare. And the standard model actually predicts how many different ways you could actually make the Higgs boson and how rare each of those channels would be. So the most likely way that's going to happen, 60% of the time, is that if you create a Higgs boson, it decays into two quarks, a bottom quark and an anti-bottom quark. So for a long time, what people were trying to detect was bottom quarks.
Bottom.
So for example, say you made 1 trillion different particles in a single collision of two of these beams in a particle accelerator. Maybe 10 of those would actually be a Higgs boson that would then decay into something that we could detect. So yes, first of all, your particle accelerator has to have enough energy to make, say, 10 Higgs bosons, but it also has to have enough energy to make the 999,999,999,990 other particles that are made in that big particle soup that comes out of one of those collisions. Plus, it's not just enough to make 1 or 10 Higgs bosons. You've got to make loads of them in order to be able to make sure that the signal, you can actually pick that out amongst everything else, every other particle that has a similar energy in that sort of range. In fact, that background of other particles with those energies, you could really call that a background noise if you want, is actually 100 billion times larger than the signal that you'd get from the Higgs boson. So it's not exactly easy. And you want to model every single event or decay or particle that could have an energy in that regime that you're searching in. And then you want to simulate how many of those events would happen, and then you'd count all those events, and then any signal you got above that, you'd know would be the Higgs boson. But of course, they didn't know what energy or mass regime to do that in. So really, what the focus turned to in the 2000s was ruling out areas that it couldn't be, drilling down those energy ranges and saying, nope, it's definitely not under there because we've accounted for everything and we don't see any extra signal. Now, that's exactly what the LEP managed to do in 2001. It ruled out any energy under 115 giga-electron volts. Now, what they didn't know at the time was that although the LEP had been designed maybe to produce the Higgs boson, the electrons and positrons that were being collided in that, which is an electron and its antiparticle, they're very light particles. And the Higgs boson, it likes heavy things. So it was extremely unlikely that you would ever have made something with the electron and positrons that were being collided together in the LEP. After this, though, the LEP was actually dismantled to make way for the equipment for the Large Hadron Collider. The exact same tunnel, but with much better particle accelerator technology. So better magnets that would give you more control over the beam and allow you to accelerate up to much higher speeds and energies. It was an experiment that was specifically designed to detect the Higgs boson, and it was done really well as well because they put 2 detectors in there, Atlas and CMS, that worked independently without talking to each other, so they could get really reliable, reproducible science out of it to make sure that if they did detect anything, then it was the Higgs boson. But obviously there was then a gap between the LEP being switched off and the LHC being switched on of about 7 years. So in 2004, the tevatron was the most likely place that the Higgs boson was going to be found, if they could find it. And you can bet the team there really wanted to be the people that found it. So they spent a lot of their efforts, again, sort of drilling down on those energy ranges that it wasn't to try and get an energy range that it was. So that by 2007, they drilled it down to have somewhere in the range of 117 giga-electron volts to 153 giga-electron volts. Then in 2008, the LHC was switched on for the first time. And if you remember that day, you will remember like mass hysteria in the media that they were going to create this giant black hole by accelerating these protons around. And again, this was because probably it was the first time that people had ever really come across this idea of particle accelerator, but in reality it was just one step up this sort of energy ladder of particle accelerators. It really wasn't that different from the tevatron that had been in use since the 70s in the USA. When that first switch on happened, 2 proton beams both went around the circular tunnel at energies just under a teva electron volt. So unprecedented energy levels, even with its first switch on, you know, before all those upgrades came. But unfortunately, a very small error with its magnets that maybe caused a little bit of an explosion shut it down for a year or so. In that time, obviously, the tevatron was back to being the most likely place that you could detect the Higgs boson. I think at the time they even sort of confidently stated that by the end of the decade, they had a 50% chance of detecting the Higgs boson. You know, rumors were flying all over the internet in 2009 that they had actually done that, but they were proved to be false. I guess that was 2009's version of fake news. Oh, to go back to simpler times like that. But with the LHC magnet problem soon fixed, in 2010, the LHC was back up and running with a combined beam energy of 7 TeV, almost 4 times greater than anything the tevatron had ever been able to achieve. The LHC also had much more control over its beams because the accelerator technology had just advanced so much in that time. It gave them much more precision when bringing the beams together, much more control. It meant that more collisions came out when any of the beams were ever brought together. More collisions meant more rare events would be produced. More rare events being produced mean that there'd be more chance of trying to spot that signal from the Higgs boson. The tevatron just couldn't compete with that, unfortunately. And so at the end of 2011, it did its last collision and was eventually shut down. The LHC wasn't idle in that time. Obviously, they'd been doing lots and lots of collisions themselves. They'd managed to drill down their energy regime once again where the Higgs boson could be found. So that by end of 2011, there was rumors flying again that some signal had been found, but obviously it wasn't high enough above that background noise for them to announce it to the world yet. But then in July 2012, there was 3 very exciting days for the search for the Higgs boson. The first came on the 2nd of July 2012, probably announced them because CERN had announced they were doing a press conference on the 4th of July and people were very excited for what they had to say. But on the 2nd of July, the tevatron actually announced what it had found from sort of its last gasp of collisions that it was done in 2011. So the team there actually analysed 50 trillion collisions that had happened in the space between 2001 and 2011. And they confirmed that they actually had found a signal that was in the energy regime of 115 to 135 giga-electron volts. But the thing was, that signal, although it was there, it wasn't what's called statistically significant. So there was a 1 in 550 chance that that was actually not real, that signal. Now that kind of probability, we put a number on that that's to do with sort of the standard deviation. We call it sigma. It's 2.9 sigma. That would be enough for astronomers. For astrophysicists, we'd be like, hey, we found it. We've definitely found something that's a discovery. Particle physicists, though, real sticklers for discoveries. And so they will not announce that anything has been found until they reach the 5 sigma level. That means that there'd be a 1 in about 3 million chance of any signal that was seen not being real. But of course, CERN had their press conference scheduled for the 4th of July 2012. And so we didn't really have to wait long for that 5 sigma announcement. This press conference, everyone from Peter Higgs and Francois Engelbert was invited. So the hype was definitely there. People really knew what was going on. And it was there that the 2 teams that have been working independently on the 2 detectors, the ATLAS detector, the CMS detector, both announced that they had found a signal in their data way above the background noise, a 5 sigma significance of this bump at about 125 giga electron volts, which could only be explained by the existence of a new boson. This is possibly one of my favorite GIFs I've ever seen come out of CERN. It shows you how the signal actually built up over time. That's sort of the black data points there. And then the histograms underneath show you sort of the expected amounts from the model of how many of those different decay tracks would produce particles of those energies. And so any difference between those black points and the histograms is essentially the signal from the Higgs boson. And that's what they presented in their papers, where they showed that nice little bump at 125 giga electron volts that was like, oh, there's the Higgs boson. And this day was practically Christmas come early for the people who worked at CERN. And you can bet when I went over there, I wanted them to tell me everything that they could remember about that fateful day.
One of the most exciting days of my life. Okay, I mean, there was the tension of building up, because there was a will they, won't they for a while. Okay, nobody, and it came very, very fast. But that day, okay, was just like, I sort of regret this now. I didn't sleep overnight on the hallways like a lot of people did.
Did they? Well, like a massive big slumber party kind of
Massive big slumber party, okay. A lot of the UK students were doing that. Huge party, waiting to get into the lecture theatre.
We knew that the announcement was going to happen. I mean, there was an announcement in 2011 with some updates, and we knew it was a massive thing. And some of my friends said, why don't we try and get into the room? And we knew the only way of getting into the room would be the first people at the queue outside. So we turned up at midnight the night before the announcement, and we had snacks, we had laptops with movies, like pillows and blankets, and we camped there all night. We were about 10th or 11th into the room.
Wow.
So I was right at the back in the middle and got to watch the whole thing live. So we had, I think, an hour talk from each of the experiments, and then at the end, the DG at the time, Rolf Hoyer, was like, I think we've got it. Nice. And there was cheers, and I mean, there's this famous photo of Peter Higgs with teary eyes, because he got to see his theory that he worked on with other theorists come true. Very inspiring as a young scientist to have been able to be there and to feel part of the moment, and then to go on to work on the Higgs myself afterwards. It was very special. Yeah. And then we celebrated in the restaurant here at CERN afterwards, and people knew which ones the Brits were, because we had a bottle of Pimm's on the table to celebrate. Yeah.
The way we celebrated was we had a Higgs BBQ, okay, with the invite.
That's my favourite pun ever.
Yes. And this is how we celebrated Higgs Dependence Day.
No, I spoke too soon. Higgs Dependence Day is my favourite pun ever.
Yes.
Editing Becky here. You're going to hear me refer to Francois Engelbert as Francois Engelbert throughout the rest of this video. He's not Engelbert Humperdinck, Becky. Get it right.
It didn't take long for more celebrations to come around, because in 2013, the Nobel Prize in Physics was awarded to Peter Higgs and Francois Engelbert for their prediction of the Higgs field and the Higgs boson, nearly 50 years before it was experimentally confirmed. It was a bit controversial at the time, because there was actually 6 people on those 3 papers that were published in 1964, plus then obviously the thousands and thousands of people that had worked at CERN on the ATLAS detectors, the CMS detector, building the LHC, of course the Tevatron team as well, which were involved in really drilling down those energy ranges so the LHC knew where to look. That's probably over like tens of thousands of people, and yet the Nobel Prize can only be given to a maximum of 3 people. Doesn't really seem relevant for the way that modern science works. But what now, though? We obviously don't know everything there is still to know, otherwise particle physicists would all be out of a job, obviously. So what questions are particle physicists still asking?
Now, back in 2012 when we discovered it, you notice the paper does not say it's the Higgs boson. No mention of is not the Higgs boson.
Okay.
Because nobody knew it was the Higgs boson at the time. We just knew there was a new scalar particle which had spin not equal to 1.
Okay.
And that was the discovery. But it kind of looked like the Higgs boson, quacked like the Higgs boson, so we were kind of quite excited. The scientific standard is much higher to say, because I mean, it really was very clearly the Higgs boson, but scientifically we hadn't proved it.
Right.
So the first thing we had to do is we had to figure out that it was the Higgs boson, and measuring how it decays to different particles. Because the Higgs boson the decays are completely fixed. It's very well predicted how exactly it'll behave. It's completely, the theory is very good. So we had to measure it, check that it was a spin zero particle, that it decayed in the right things, and it took us to 2013. Okay, actually, I was in the conference where we decided it was a Higgs boson at this point.
Okay.
It was not the Higgs boson at this point, but it was a Higgs boson. It made the criteria for Higgs boson, and then we've been looking at trying to actually measure its decay to other channels, because just because it decay, so the Higgs boson gives mass to vector bosons, the W and Z, and it also gives mass to fermions. So like electrons, muons, quarks, and it took a while to actually see it decaying to fermions, and we weren't sure if this was a Higgs boson only gave it. This was a Higgs boson that only gave it to electroweak symmetry, and there was another Higgs boson that generated for fermions until we actually saw it decay. And in fact, it took us a little while to see it. There was evidence in Tau Tau and BBB, but it took a while to see it. And I think 2018 is when we actually first saw it going to bottom quarks. Which again is 60% of the decays, but it's so hard. They're so hard to find. So again, showing that we actually can measure at that point, it was very clear that it was now the Higgs boson, and we're still trying to measure all the other branching properties of it, seeing it, checking all the decays that they match up the standard model. And the reason for this is the Higgs boson is the wonderful portal to new physics.
And one of the biggest driving factors actually for new physics is the galactic rotation curve, obviously dark matter. So everything's spinning much too quickly, and if we measure the mass of the luminous matter there, it doesn't quite work. And you have to put in this non-luminous, i.e. non-interacting with electromagnetic field matter to hold everything in with an opposite gravitational effect. So we look for things like this, and supersymmetry is one of many possible extensions. You know, there are dark matter models and things like this, and then exotic physics, so very exotic states of matter, very unusual combination of quarks. So we have a lot of work to do. I mean, there's so much left to do in the future. Before, everything was quite theory-led, so the standard model was excellent, and the theorists were able to say, oh, there's probably a top quark, and Murray Gell-Mann was able to say, oh, there's probably all of these mesons, and then in the 70s and 80s there was an explosion of all these discoveries, because he was right, you know, and theoretically predicted this. And the same with the Higgs, it was predicted. So we knew that it should be of some mass, and it has to be there somewhere. But now we know what's wrong with the standard model, but not really how to fix it.
So particle physics is doing all right. We've got this wonderful model, but we've so far explained 4% of the observable universe. And
us astronomers are like, we're waiting, guys.
Yeah, exactly. So there's room for improvement, and we're also missing a fundamental force, gravity. So there's work to do. Okay, the standard model is not complete. So we think there's new physics out there, and WIMPs, dark matter candidates. We think there's a heavy particle out there which is forming what we call as dark matter, which we see in gravitational effects. Dark matter obviously has mass. Higgs boson generates mass. Higgs boson should like dark matter. This is so now we know exactly where to look for the Higgs boson. We can start seeing it. Is it decaying to something? Is it decaying to dark matter?
Wow, that'd be really cool.
And yeah, this is quite challenging because we can't see dark matter.
Yeah.
So it's Higgs to invisible.
Never thought of that. That's so cool.
So what we need is we need data. We need number of Higgses. So Higgs decays. These decays we're looking at are rare, and we need a lot of Higgs for it. And luckily, we've got the high luminosity LHC, which is our next thing coming up, 2027. Okay, I think, although the schedule is changing. Yeah. So coming up in a few years, and right now we're preparing for that right now. Because it's the LHC right now is still actually early in its program. We've taken 5% of the data we plan to take of the LHC program.
Wow.
So we have a lot coming.
The most incredible thing about being here is knowing that you are surrounded by the history of the Higgs boson. In essence, like, it's not just that, I think people like Engler and Higgs could have walked these halls, but it's the other thousands of minds that have walked these halls throughout the development of the theory and then the experiments and leading to the discovery of Higgs as well. This place is just so incredibly inspiring, and it almost makes you wonder, like, what is the future going to hold in terms of our understanding of the universe, and what will particle physics bring us next? Before we get to the bloopers, I just want to say a massive thank you to CuriosityStream, who are the sponsor of this week's video, for essentially funding my trip out here to CERN. CuriosityStream is a streaming service for documentaries and non-fiction films on pretty much any subject that you can imagine. From science to history to art to anything that you're really interested in. If you want to hear more about particle physics after watching this week's video, then they've got you covered. Usually CuriosityStream's plan is just $20 a year. However, with their new Stay In and Stay Curious campaign, because let's face it, none of us are going anywhere, we're all under quarantine right now, they have dropped this to just $12 a year. Go to curiositystream.com/Dr. Becky, that's DRBECKY, to access the world's finest documentaries and non-fiction series. And best of all, for my subscribers, if you enter the promo code Dr. Becky, DRBECKY, during the sign-up process, you'll get your first 30 days completely free. By 1995, the Tevatron at Fermilab had actually managed to... By 1995, the Tevatron at Fermilab... In 2001, that's exactly what the LEP did. It ruled out any energy under 115 giga-electron volts and was shortly switched down? That's not a word. It was only actually in the press conference that anyone Tevatron. I can't get over the name. Like, it just, to me, it sounds like it's a transformer, right? Like that it's like Megatron's best friend, Tevatron. I'm just picturing this huge big lorry thing just like up to this big, like giant robot thing that's like, hello, I am Tevatron. I have come to save Earth. Don't blame it on the sunshine. Don't blame it on the moonlight. Don't blame it on the good times. Blame it on the Higgs Boson.